Imagine two surveyors sent to map the same field. The first walks the ground with a chain and records what she finds there. The second may not measure anything. She is handed only an inventory of the field's contents, its stones, its water, its heat, and told to work out the shape of the ground from that alone. Both come back with a map. Both maps give distances and curvature, and when you lay one over the other, almost every line matches. Almost. Somewhere below anything any instrument has detected, the two are out of register. In 2025, a mathematician in London proposed that the strain between two such maps is not a curiosity, it is gravity. It is why everything you have ever dropped fell. So, did this physicist find a new origin for gravity? By the end of tonight, you will know exactly what she found and exactly what she did not. Before we begin, if slow walks around very large questions are how you like to fall asleep, a like or a subscribe would mean a great deal to me. It helps me keep making these. Now, let's begin. There are two answers to the question of how far apart things are in the room you are lying in right now, and nobody has ever told you about the second one. The first answer is the one physics has been giving for over a century. Space-time has a geometry. That geometry is described by an object called the metric, and the metric is, in the plainest possible terms, the thing that tells you the distance between any two nearby points. Give me the metric, and I can tell you how far it is from your hand to the edge of the bed. I can tell you how long a second lasts here, compared with a second somewhere else. I can compute the curvature of space in this room, and from that curvature, I can work out exactly how a dropped object will fall. Everything Einstein gave us runs through that one object. The metric is the geometry, and the geometry is gravity, and for 109 years, that has been the whole story. But there is a second way to answer the same question, and it is the one this entire episode is about. Instead of asking what the geometry is, you can ask what the matter is doing. You can look at the fields sitting in this room, the physical stuff, whatever it happens to be, however it happens to be arranged, and you can build a geometry out of that. Not measure the geometry. Build one. Construct a description of distance and curvature purely from the content of the space, rather than from the shape of it. And when you do, you get a second object with the same kind of structure as the first, a second metric, a second answer to how far apart things are. It helps to make that concrete. Imagine two surveyors sent to map the same field. The first one walks the ground with a measuring chain and records distances directly. This is the true metric, the geometry as it is. The second one is not allowed to measure anything. She is given only an inventory of what is in the field, where the stones are, where the water sits, how the heat is distributed, and told to reconstruct the shape of the ground from the contents alone. Both of them come back with a map. Both maps describe distances. Both maps describe curvature, and when you lay one over the other, the lines almost line up. They almost do. Here is the part that took me a while to sit with properly. The two answers do not agree. They do not have to agree. Nothing in Einstein's work requires them to agree. Nothing in quantum mechanics requires them to agree. In fact, for most of the last century, nobody was even asking the question, because nobody had written down the second geometry in a form precise enough to compare with the first. The two descriptions were never laid side by side. In August of 2024, a paper appeared on the physics preprint server that laid them side by side and asked a question that, once you hear it, is very difficult to unhear. What if the disagreement between those two geometries is not a curiosity? What if it is not an artifact of writing things down in an awkward way? What if the disagreement is gravity itself? The paper is called Gravity from Entropy. It was submitted on the 26th of August, 2024, accepted on the 27th of January, 2025, and published on the 3rd of March, 2025, in Physical Review D, Volume 111, Article 066001. It is 17 pages long. It has one author. There is a detail about that paper I find quietly revealing, and it takes about 10 seconds to explain. When you post a paper to the preprint server, you have to file it under a subject category, the way you would shelve a book. Most papers get one. This one got 4. It is filed under general relativity and quantum cosmology, and under statistical mechanics, and under high-energy physics theory, and under quantum physics. 4 different rooms of the building, all at once. Before you read a single line of it, the filing system is telling you that whoever wrote this was not standing where the people who normally write about gravity stand. Her name is Ginestra Bianconi. She is a professor of applied mathematics at Queen Mary University of London, in the School of Mathematical Sciences, and she has spent essentially her entire career on something else: networks. The mathematics of nodes and links, of how the shape of a connected system determines what happens on it. She has more than 20,000 citations to her name, and, until very recently, almost none of them had anything whatsoever to do with gravity. I want to be careful here, because this is the kind of story that gets flattened in the telling. This is not an outsider who wandered in and overturned physics. She is an extremely accomplished scientist, a fellow of the American Physical Society, an elected member of the European Academy of Sciences, someone whose name is attached to a standard model of network growth that thousands of people use. But she is an accomplished scientist in a field that most theoretical physicists regard as adjacent, as applied, as useful, as not quite where the fundamental questions live. And then she walked into the oldest unsolved problem in physics, carrying tools that almost nobody there uses. So let me tell you what she proposes, without yet telling you how it works. In physics, underneath every set of laws, there is something called an action. The action is a single quantity that, when you demand that it be as small as possible, or, more precisely, that it be stationary, hands you back the laws of motion. It is one level beneath the equations. Newton's laws come from an action. Maxwell's equations come from an action. Einstein's field equations come from an action, called the Einstein-Hilbert action, written down in 1915. If you want to change the laws of physics, the honest way to do it is to change the action, and then see what equations fall out. Bianconi's proposal is that the action for gravity is a measurement of exactly how much those two geometries disagree. That is it. That is the idea. Not a new force, not a new particle, not an extra dimension, a comparison between two descriptions of the same place, and a claim that nature is doing whatever minimizes the difference between them. And the specific way she measures the disagreement is the reason the paper is called what it is called. The measurement is a kind of entropy, not the entropy you have heard of, not the thing that supposedly means disorder, not the thing about your bedroom getting messy, a different quantity, with the same family name and a very different character, and by the end of this episode, you will understand exactly why it had to be that one and not the other. If she is right, then gravity is not something acting on you. Gravity is a strain. It is what a disagreement feels like from the inside. And that brings us to the question this episode exists to answer, which I am going to pose now, and then deliberately refuse to answer for the next 2 hours. Did she find it? Did this physicist actually find a new origin for gravity? Because that question has a real answer, not a vague one, not a hopeful one, not a shrug. 18 months have passed since publication. 3 research groups on 3 continents have taken the theory into places she never took it, into black holes, into the first fraction of a second after the Big Bang, into the thermodynamics of space-time itself. One person has examined whether the theory is even stable, and found something that may sink it. There is a scoreboard now, and by the end of tonight, you will have seen every entry on it. But we are not ready for the answer yet, Before you can judge whether gravity can be made of entropy, you need to know what entropy actually is. And almost everything you have been told about entropy is a metaphor that was wrong when somebody invented it 150 years ago, and has been quietly wrong ever since. So let the room settle around you for a moment. The ceiling above you, the floor beneath the bed, holding you up. The ordinary, uneventful, completely reliable fact that things fall down and stay down, which has been true every second of your life, and every second of every life before yours. Two descriptions of that room, overlapping, not quite matching. Let us find out where that word came from. The word entropy is 161 years old, and the man who invented it did not know what it counted. That is not a criticism of him. It is a fair description of the situation. He knew there was a quantity. He knew it had a definite value for any system you cared to name. He knew that in any real process, it went up and never down. He could calculate it. He could use it. He simply could not tell you what it was a measurement of, because the answer to that question required atoms, and in 1865, the existence of atoms was still an open and rather contentious matter. But to understand where the word came from, we have to go back 40 years earlier, to a young man in Paris who was working on a much more practical problem. His full name was Nicolas Léonard Sadi Carnot, and he was named after a medieval Persian poet, Sadi of Shiraz. He was born on the 1st of June 1796 in Paris, the son of a member of the French Directory. He entered the École Polytechnique in 1812 at the age of 16, which was the minimum age the institution allowed, and he was taught there by Poisson, by Ampère, and by Arago, three of the most formidable physicists in Europe, all in the same building, all teaching the same teenager. The problem he took up afterward was steam engines. Specifically, how efficient can an engine possibly be? Not how efficient are our engines, which was an engineering question with an engineering answer, but what is the ceiling? Is there a limit written into nature that no amount of cleverness can climb past? The answer, it turns out, is yes, and Carnot found it. On the 12th of June, 1824, he published a book called Réflexions sur la puissance motrice du feu, Reflections on the Motive Power of Fire. He was 28 years old. The book runs to 118 pages in the original French. It was the only work he published in his entire lifetime, and buried inside it is the seed of what would become the second law of thermodynamics, the single most reliable statement in all of physics. The version of the story you usually hear is that nobody read it. That is not true, and the true version is sharper. 6 weeks after publication, on the 26th of July, 1824, a man named Pierre Girard delivered a long review of the book to the Académie des Sciences in Paris. The review was positive. It was thorough. It laid out Carnot's theorems and his conclusions in full. And, as the historians of mathematics at St. Andrews put it in their assessment of that review, it did not comment on the highly original reasoning that Carnot had employed. The most important idea in the book went straight past the man reviewing it. So the book was not ignored. It was read, praised, summarized accurately, and then dropped. Which is, if you think about it, a far more unsettling way for an idea to be lost. Carnot's argument only entered physics properly in 1834, 10 years later, when Émile Clapeyron reformulated it in analytic form and presented it graphically. And here is the detail that closes the circle. Rudolf Clausius, the man who would give us the word entropy, learned about Carnot's work through Clapeyron's version. Not through Carnot's book, through somebody else's summary of somebody else's summary. Carnot himself was not there to see any of it. In June of 1832, he fell ill. He had not fully recovered when the cholera epidemic reached Paris, and when he contracted it, he died within a day. He was 36 years old. And then something happened that I want you to sit inside for a moment. Under the public health regulations of the epidemic, the belongings of cholera victims were to be destroyed. So the men came into the room, where a 36-year-old man had been dead for less than a day, and they began carrying things out. The bedding, the clothes, and then the papers. Picture that. Notebooks in a small, careful hand, pages of working, sketches of experiments involving the heating of fluids by friction, experiments that would not actually be performed by anyone for another 20 years, when James Joule finally got round to them and changed physics doing it. Pages in which Carnot is quietly working through the idea that heat is not a weightless fluid at all, which is remarkable, because the caloric theory of heat as a weightless fluid is the foundation his own published book stands on. He was in the process of demolishing his own scaffolding, in private, in his notebooks, and nobody knew. None of it is read. Nobody opens a single page to check. It goes onto the fire because it was in the room, and the regulations say what was in the room burns. Nearly all of his papers went that way. A handful survived. One separate manuscript of his, written between 1822 and 1823, was not discovered until 1966, 134 years after his death, sitting somewhere, waiting. There is an irony in Carnot's work that I think is genuinely one of the most useful things in the history of science, and it is this. He built the foundation of the second law of thermodynamics on top of a theory of heat that was simply, factually wrong. Caloric does not exist. There is no weightless fluid of heat flowing from hot bodies to cold ones. And yet the conclusion he reached from that false premise is correct, has never been overturned, and underpins every engine, every refrigerator, and every power station on the planet. The scaffolding was wrong. The building is still standing. Now we come to the word itself. Rudolf Clausius introduced it in 1865 in a paper in the Annalen der Physik und Chemie, volume 125, page 353. And unusually for a scientific coinage, he explains exactly why he chose it. In translation, here is what he wrote. If we wish to designate S by a proper name, we can say of it that it is the transformation content of the body, in the same way that we say of the quantity U that it is the heat and work content of the body. However, since I think it is better to take the names of such quantities as these, which are important for science, from the ancient languages, so that they can be introduced without change into all the modern languages, I propose to name the magnitude S the entropy of the body, from the Greek word for a transformation. And then he adds the sentence I find the most human thing in the whole passage. I have intentionally formed the word entropy so as to be as similar as possible to the word energy, since both these quantities, which are to be known by these names, are so nearly related to each other in their physical significance that a certain similarity in their names seemed to me advantageous. He built the word to rhyme, on purpose. He had a perfectly serviceable German alternative, Verwandlungsinhalt, transformation content, and he set it aside in favor of a Greek construction specifically engineered to sound like the word it would spend the next century standing beside. And he closed that same paper with two sentences that have been quoted ever since, and that are, as far as anyone can tell, still true. The energy of the universe is constant. The entropy of the universe tends toward a maximum. That is 2 lines. It is the whole of thermodynamics, and a claim about the fate of everything. He is careful to credit William Thomson, later Lord Kelvin, with having first drawn attention to what the second line implies, that the universe is therefore persistently approaching a final state and will not be turning back. I want to flag something about the origin of all this, because it matters for where we are going. Thermodynamics did not begin as a search for fundamental truths about the universe. It began with heat engines. It began with the extremely practical question of how much work you could get out of a given amount of coal during the Industrial Revolution, asked by men who needed the answer for commercial reasons. The second law of thermodynamics, the law that tells us the universe has a direction, that time does not run backwards, that the whole thing is winding down toward a final state, arrived as a byproduct of trying to build a better steam engine. And it arrived in a particular form. Clausius could tell you the rule. He could not tell you the mechanism. That distinction between a law you can state and a law you can explain is going to come back later in a much more important context, because it is precisely the distinction Bianconi points to when she explains why her theory looks the way it does and other entropic theories of gravity do not. So by 1865, there is a name, a symbol, a rule, and a prophecy. What there is not, yet, is an explanation. Clausius could tell you that entropy increases. He could not tell you why, and he could not tell you what the quantity was measuring. That answer arrived 7 years later, from a man in Vienna, and it cost him more than any physicist should have to pay. Here is the answer Ludwig Boltzmann gave, and it is still the answer. Take any system you like, a gas in a box, a cup of coffee, a room. Now write down everything you know about it at the large scale, its temperature, its pressure, its volume. That description is called the macro state, and it is a very short list, a handful of numbers. Now ask a different question. Given only those numbers, how many distinct microscopic arrangements of the individual parts would produce exactly that large-scale description? How many ways could the individual molecules be positioned and moving such that if you measured the temperature and the pressure, you would get the values you just wrote down? That count is enormous, absurdly, incomprehensibly enormous. And the entropy is the logarithm of that count. That is what entropy is. That is all it is. It is not a substance. It is not a fluid. And I want to be direct about this, because it is the single most widespread misconception in popular science. It is not disorder. Entropy is a measure of how much you do not know about a system, given what you do know about it. Please hold on to that sentence, because everything in the second half of this episode depends on it. Entropy is ignorance, quantified. It is not a property of the system in isolation. It is a property of the relationship between the system and your description of it. Let me make that concrete with something you can hold. Take a deck of cards. If I tell you the deck is in factory order, ace through king, suit by suit, I have told you everything. There is exactly one arrangement consistent with that description. The count is 1, the logarithm of 1 is 0, and the entropy is 0. There is nothing left for you not to know. Now let me shuffle it and tell you only that it is shuffled. The number of arrangements consistent with that description is roughly 8, followed by 67 zeros. That is more than the number of atoms in our galaxy. The entropy of that description is enormous. And notice that nothing about the physical deck has changed in any fundamental way. It is the same 52 pieces of card. What changed is how much I told you. What changed is how much you do not know. This is why the disorder metaphor causes so much trouble. A shuffled deck is not more disordered in any physical sense at all. Every specific shuffled arrangement is exactly as specific as factory order. There is nothing messier about it. What there is more of them. Vastly more arrangements that we would all agree to describe with the single word shuffled. Boltzmann published the result that made this into physics in 1872. It is called the H theorem, and the claim it made was extraordinary, that he had derived the second law of thermodynamics from mechanics, that the tendency of entropy to increase was not a separate rule bolted onto physics, but a consequence of the ordinary motion of particles bouncing off each other. The objections came almost immediately, and they came from inside the house. In 1876, Joseph Loschmidt raised what is now called the reversibility objection, and it is devastating in its simplicity. The laws of mechanics are time reversible. Take any motion of any set of particles, reverse every velocity, and you get another perfectly legal motion. So for every trajectory on which entropy increases, there exists a mirror trajectory on which it decreases. You cannot derive a one-way result from two-way laws. Something else has to be doing the work. And here is the part that gives the objection its weight. Joseph Loschmidt had been Boltzmann's teacher. He was later his colleague at the University of Vienna. He was, by every account, his friend for life. The most serious technical challenge to Boltzmann's central achievement came from someone who loved him. Then in 1896 came a second objection, from a young mathematician named Ernst Zermelo, who at the time was working as Max Planck's assistant in Berlin. Zermelo pointed to a theorem of Poincaré's. A bounded mechanical system must eventually return arbitrarily close to any state it has previously occupied. Wait long enough, and the gas in the box will spontaneously gather itself back into the corner it started in. If that is true, entropy cannot increase forever. The second law cannot be absolute. Boltzmann had answers to both. The recurrence times are so long as to be meaningless, vastly longer than the age of the universe, for any system with more than a handful of particles. The reversibility objection is met by noting that the low entropy states are so overwhelmingly outnumbered that a system prepared in one will, with probability indistinguishable from certainty, move toward the crowded region. But answers are one thing, and acceptance is another, and acceptance did not come. He spent 30 years arguing for the reality of atoms, against colleagues who regarded them as a useful fiction at best, and a philosophical embarrassment at worst. His entire framework required them. If atoms were not real, there was nothing to count, and if there was nothing to count, his definition of entropy meant nothing at all. On the 5th of September 1906, while on holiday with his wife and youngest daughter at Duino, a village on the Adriatic coast, north of Trieste, where the limestone comes down to the sea, Ludwig Boltzmann took his own life. He was 62 years old. He was going blind. He had been suffering from what was then called neurasthenia, and from what we would now recognize as severe depression, and the long hostility of his colleagues is generally counted among the contributing factors. Within a few years, Jean-Baptiste Perrin's experimental work on Brownian motion ended the argument about atoms permanently and completely. The thing Boltzmann had spent his life insisting on was settled, in his favor, just after he stopped being alive to hear it. His grave is in the Zentrale Friedhof in Vienna. Carved into the stone above it is the equation S equals K log W. Entropy equals a constant times the logarithm of the number of microstates. It is the most famous formula in statistical mechanics, and one of the most famous in all of physics. Boltzmann never wrote it in that form. He never introduced the constant either. The constant, now universally called Boltzmann's constant, was isolated by Max Planck in 1900 in the course of the black-body radiation work that would accidentally begin quantum mechanics. Planck gave the constant its symbol, computed its numerical value, and later remarked, with what I have always read as a certain dryness, that the constant is often referred to as Boltzmann's constant, although, to his knowledge, Boltzmann himself never introduced it. The sentence on the gravestone was written by somebody else. And there is one final turn, which happened well within living memory. On the 20th of May 2019, following a decision taken by the General Conference on Weights and Measures in November of 2018, the Boltzmann constant stopped being a measured quantity. It is now a defined one. Its value is exactly 1.380649 times 10 to the minus 23rd joules per Kelvin, with no uncertainty, forever, because we said so. The Kelvin is now defined by fixing it. To justify that move, the metrologists had to demonstrate that at least one measurement technique could reach an uncertainty below 1 part in a million, and that a fundamentally different technique agreed to better than 3 parts in a million. The most precise values came from acoustic thermometry, from measuring, with extraordinary care, the speed of sound through a gas. Open a physics textbook from the 1980s, and the constant reads 1.38066, 2 times 10 to the minus 23rd, with error bars. Today the error bars are gone by international agreement. So here is the arc, compressed. The quantity was found in a book about steam engines in 1824. It was named in 1865 by a man who did not know what it counted. It was given its meaning in 1872 by a man whose colleagues rejected the atoms it required. The equation on his tombstone was written by someone else, and the constant in that equation was finally frozen to an exact decimal by committee in 2019. It took 154 years to get from the name to the number. And after all of that, after Carnot and Clausius and Boltzmann and Planck, Bianconi's action is not this entropy. It is a different one. Everything you have just learned about entropy is true, and it is not the quantity Bianconi's theory is built on. Boltzmann's entropy counts. It takes one system and it counts the arrangements. There is a different quantity in the same family that does something else entirely. It compares. Here is how it works, without a single equation. You hold a model of how the world is. Some expectation, some distribution, some picture of what is likely and what is not. Then the world does something. And the question this quantity answers is, how surprised should you be? How much did you just learn? If your model was excellent, if reality behaved more or less exactly as you expected, then you learned almost nothing, and the quantity is close to zero. If your model was badly wrong, if the world did something your picture said was nearly impossible, then you learned a great deal, and the quantity is large. It is called relative entropy. It is never negative, and it is exactly zero in one situation only, when the two descriptions coincide perfectly, when your model and reality are the same thing. There is one more property worth having, because it turns out to matter enormously. Relative entropy is not symmetric. The surprise of finding B when you expected A is not the same number as the surprise of finding A when you expected B. That sounds like a defect. It is not. It is exactly right. Being wrong about the world is a different operation from the world being wrong about you, and any honest measure of the mismatch has to keep track of which direction you are looking. Now let me trace where this object came from, because the lineage is a genuinely strange one. It begins, more or less, in 1948, with a paper called A Mathematical Theory of Communication by Claude Shannon, published in the Bell System Technical Journal, Volume 27, in 2 parts, pages 379 to 423 in July, and 623 onward in October. That paper invented information theory, essentially from nothing. It is where the word bit first appears in print. The historian James Gleick rated it the most important development of 1948 and placed the invention of the transistor second. There is a famous story about how Shannon chose the name for his central quantity, and I am going to tell it and then immediately take it away from you. The story, as it was published by Myron Tribus and Edward McIrvin in 1971, goes like this. Tribus asked Shannon whether he had not worried that borrowing the word entropy would cause confusion with thermodynamics, and Shannon replied that John von Neumann had told him to call it entropy for 2 reasons. First, because the mathematical form was already used in statistical mechanics under that name, and second, because nobody really knows what entropy is, so in a debate you will always have the advantage. It is a wonderful line. It has been quoted in probably every popular book on information theory ever written. The authors of the definitive Shannon biography, having gone looking for it, write, "Almost certainly, this conversation never happened." Consider the chain. Tribus was at MIT for a week in April of 1961 and had a conversation with Shannon. He published his recollection of that conversation 10 years later, in 1971. The conversation was about a remark supposedly made by a third person more than a decade before that. It is precisely the kind of story that improves every time it is told. I am telling you because it is genuinely part of the folklore and you will encounter it. I am flagging it because a story being good is not evidence that it is true, and the habit of noticing the difference is worth more than the story. 3 years after Shannon, in 1951, Solomon Kullback and Richard Liebler published an 8-page paper in the Annals of Mathematical Statistics, Volume 22, pages 79 to 86, called On Information and Sufficiency. That is where relative entropy enters mathematics as a formal object with a name. 8 pages. If you see it dated to 1953 somewhere, that is a common citation error. It is 51. Then, in 1962, a Japanese mathematician named Hisaharu Umegaki carried the idea into the quantum world. The paper is called Conditional Expectation in an Operator Algebra, Part 4, Entropy and Information, published in the Kodai Mathematical Seminar Reports, Volume 14, pages 59 to 85. Notice what that means. The concept that would one day be proposed as the action for gravity, the quantity that might tell us why things fall, first appeared as a technical result in Part 4 of a series of papers about conditional expectation in operator algebras. It was not announced. It was not a breakthrough. It was the 4th installment of a functional analysis project, and it sat there for 62 years. And then there is Araki. Fusihiro Araki, working in Kyoto, Publicative Entropy of States of von Neumann Algebras in 1976, with a sequel the following year. And he is the name that actually matters for this story, for a reason that takes about 90 seconds to explain, but is worth every one of them. Umegaki's quantum version requires 2 things to exist, a density matrix and a trace. Those are technical objects, and in most of quantum mechanics, they are perfectly available. But the mathematical structures that describe quantum fields inside a region of spacetime, the algebras you actually need if you want to talk about the physics of a volume of space, are a particular kind called Type 3 von Neumann algebras, and Type 3 algebras have no trace, they have no density matrices. Umegaki's definition simply does not apply there. Araki's construction, built on something called the relative modular operator, works anyway. He proved that his version is strictly positive, that it behaves well under limits, that it is convex, and that it never increases when you enlarge the region you are looking at. He rescued relative entropy for the setting where quantum field theory actually lives. Bianconi cites him directly. In her paper, she writes that the quantum relative entropy proposed in the work is strictly related to the Araki quantum relative entropy for von Neumann algebras. Araki is the mathematical ancestor. Now here is why any of this was necessary, and this is the technical heart of the first half of tonight. Take the vacuum of a quantum field, genuinely empty space, nothing in it. Draw an imaginary surface through it, dividing the space into an inside and an outside. Now ignore the outside completely and ask what state the inside is in. You might expect the answer to be empty, obviously. It is a vacuum, but it is not. The vacuum is not a product state across any spatial cut. The 2 sides are entangled with each other, and so the inside on its own is in a mixed state, and a mixed state has entropy. Empty space, cut in half, has entanglement entropy. Bombelli, Kuhl, Lee, and Sorkin worked out what that entropy is in 1986 in Physical Review D, Volume 34, page 373. 2 things came out. The first is beautiful. The entropy is proportional to the area of the dividing surface, which is exactly the behavior black hole entropy has, and which nobody was expecting from a calculation about empty space. Srednicki confirmed it numerically on a lattice in 1993. The second thing that came out is that the entropy is infinite. It is not large, it is infinite. And the reason is physical rather than mathematical. The entropy comes from correlations across the cut, so only modes sitting very close to the dividing surface contribute anything. But there is no shortest wavelength. You can pile ever shorter and shorter modes against that surface without limit, and every one of them adds. The sum runs away. Jacob Bekenstein put it plainly in his own summary. The entanglement entropy is proportional to the horizon area, just as required to explain black hole entropy, but the coefficient is ultraviolet divergent and requires renormalization by physical arguments, which in practice means you have to reach in by hand, decide where to stop, and the answer depends on where you decided. Gerard Hooft's brick wall from 1985, an artificial barrier inserted to hold the thermal atmosphere off the horizon, is the same problem wearing a different coat. So the ordinary entropy of a region of space in quantum field theory is infinite, and you cannot build a physical theory on an infinite number without cheating. And here is what saves it. The relative entropy between two states of that same region is finite, completely finite, with no cutoff required, no hand-inserted wall, no arbitrary choice. Because both states have the same divergence, the same runaway pile of short wavelength modes against the same surface, and when you compare them, the two infinities cancel exactly. They are two infinities of the same shape, subtracting cleanly. That is why Bianconi's action is a relative entropy and not an ordinary one. Not because it is elegant, though it is, because it is the only version of the quantity that is finite. The choice was not aesthetic, it was forced. Edward Witten's review article of 2018 in Reviews of Modern Physics, Volume 90, Article 045003, is the standard modern reference for all of this, and it gives the rigorous quantum field theoretic definition of relative entropy due to Araki, along with a surprisingly simple proof of its main properties. That article has one of the strangest titles in physics. It opens with the words, APS Medal for Exceptional Achievement in Research, for the mundane reason that it was commissioned in connection with a prize Witten had just received. Bianconi cites him as the person who proposed Araki entropy as the right way to capture entanglement. So, somebody had a finite quantity, a measure of disagreement between two descriptions that stays well behaved in exactly the setting where everything else blows up. The question is what you do with it. And she was not the first person to think that gravity and entropy belonged in the same sentence. The idea that gravity might be made of information has a 59-year history, and I want to walk it quickly, because the point of this part is not the individual attempts. The point is a single structural fact that all of them share, and that Bianconi's theory does not. It starts in 1967 with Andrei Sakharov. The paper is 3 pages long. It contains 4 formulas. Its title is Vacuum Quantum Fluctuations in Curved Space and the Theory of Gravitation, and it appeared in the Proceedings of the Soviet Academy of Sciences, Volume 177, pages 70 to 71. In those 3 pages, Sakharov proposed that gravity is not fundamental at all, that general relativity emerges from quantum field theory in roughly the way hydrodynamics emerges from molecular physics, that the Einstein-Hilbert action is not a law of nature, but something induced by the vacuum fluctuations of ordinary matter fields. That is 3 pages. Every emergent gravity program of the last half-century descends from them. Then, 5 years later, black holes. Jacob Bekenstein, in 1972, and again in 1973, argued that a black hole has an entropy, and that the entropy is proportional to the area of its horizon. Not its volume, its area. That is already very strange. Everything else in physics has an entropy that scales with how much stuff there is. which means volume. Then in 1974 and 1975, Stephen Hawking showed that black holes radiate, worked out the temperature, and in the process fixed the numerical factor in Bekenstein's formula at exactly 1/4. The numbers here are worth a moment. Bekenstein's own comparison, in his own words, is that a black hole with the mass of the Sun has a horizon area of the same order as the municipal area of a large city, Atlanta or Chicago, and the entropy of that horizon is about 4 times 10 to the 77th, roughly 20 orders of magnitude larger than the thermodynamic entropy of the entire Sun. Take a star, collapse it into something the size of a city, and its ignorance content goes up by a factor of 100 billion. Bekenstein also proposed what is called the generalized second law, that the entropy outside a black hole plus the entropy of the black hole itself never decreases. He formulated it 2 years before Hawking radiation was established. In effect, he predicted it, because if a black hole has a temperature, a black hole must radiate, and the generalized second law only works if it does. There is one more Bekenstein detail worth carrying, because it is the sort of thing that tells you a subject is not finished. The third law of thermodynamics, in the form Nernst and Simon gave it, says that as a system's temperature approaches absolute zero, its entropy approaches zero as well. Black holes break it. A maximally spinning, maximally charged black hole has a temperature of exactly zero and an entropy that is emphatically not zero, and that still depends on how fast it is turning. The related statement that you cannot actually reach absolute zero does seem to survive. When you feed matter into a black hole to spin it up, the process stalls at a spin parameter of about 0.998, just short of the extreme. Nature appears to have installed a governor. Nobody fully knows why. Then, 1995. Ted Jacobson, Thermodynamics of Spacetime, The Einstein Equation of State, Physical Review Letters, Volume 75, page 1260. What Jacobson did is, in my view, one of the most quietly shocking results of the late 20th century. He assumed 2 things. First, that entropy is proportional to horizon area. Second, the Clausius relation from ordinary thermodynamics, heat equals temperature times change in entropy. Then he demanded that this hold not just for black holes but for every local horizon, at every point of spacetime, as seen by an observer accelerating just inside it. And Einstein's field equations fell out. They did not come out as an assumption, they came out as a consequence. The equations governing the shape of spacetime emerged as an equation of state, the same category of law as the ideal gas law, the same kind of statement as pressure times volume equals a constant times temperature. Sit with what that implies. Nobody tries to quantize the ideal gas law. The question is malformed. Pressure and temperature are not fundamental things that could have quantum versions. They are bulk descriptions of an underlying reality made of molecules. If Einstein's equations are in that category, then 90 years of failing to build a quantum theory of gravity stops being an embarrassing technical failure and becomes a question that was never well posed. Thanu Padmanabhan spent much of his career building this out systematically, associating thermodynamic properties with horizons across a whole family of gravitational theories. His 2010 review in Reports on Progress in Physics is the standard entry point, and Bianconi cites it as the marker for the whole active direction. And then Eric Verlinde, in 2011, published On the Origin of Gravity and the Laws of Newton, arguing that space itself emerges holographically and that gravity is an entropic force, that things fall because information wants to rearrange, in the same way that a stretched rubber band pulls back not because of any force between its molecules, but because there are more ways for it to be slack than taut. He extended it in 2017 to try to explain dark matter as a consequence, which drew published objections and remains genuinely contested. I want to be clear about that. Entropic gravity is a live research program, not a settled position, and the extensions have been argued over hard. So that is the lineage. Sakharov, Bekenstein, Hawking, Jacobson, Padmanabhan, Verlinde. 6 major names, 59 years, and a great deal of very serious work. And every single one of them put the entropy on a surface. It might be a local horizon, or a holographic screen, or a cosmological horizon. In every case, the information lives on a boundary, a 2-dimensional sheet in a 3-dimensional world, and the entropy scales with the area of that sheet. There are excellent reasons for this. Bekenstein's area law points that way, holography points that way, and, more practically, a surface is where physicists know how to count. You draw a boundary, you count the degrees of freedom on it, you are done. There is another place the information could live. It could live in the volume. It could be a density at every point, spread through the bulk of space-time, with no boundary drawn anywhere and no screen required. Nobody was looking there, because nobody had a quantity you could put there that would not immediately become infinite. But we just spent the last part discussing a quantity that does not become infinite. It would take somebody who did not already know where the entropy is supposed to go, somebody trained in a completely different field, carrying different instincts, who had never been taught which parts of the problem are the respectable ones. Ginestra Bianconi took her undergraduate degree in physics at Sapienza University in Rome in 1998, working under Luciano Pietranero. She went to the United States for her doctorate, finishing at the University of Notre Dame in 2002, where her advisor was Albert Laszlo Barabasi, one of the people who essentially invented modern network science. And then she became one of them. If you have ever encountered the mathematics of networks, you have encountered her work. In 2001, with Barabasi, she published a paper in Physical Review Letters, volume 86, page 5632, called Bose-Einstein condensation in complex networks. The result is one of those things that sounds like a joke until you look at it. Bose-Einstein condensation is a quantum phenomenon in which, below a certain temperature, a large fraction of the particles in a gas collapse into a single, identical state. What Bianconi and Barabasi showed is that a growing network, a network where new nodes keep arriving and choosing where to attach, can do exactly the same thing. Under the right conditions, one single node captures a finite fraction of every link in the entire system. The winner does not just take most. The winner takes a fixed percentage of everything, forever, no matter how large the network grows. That model is now called the Bianconi-Barabasi model. It is in the textbooks. It is her name on the thing. The rest of the career reads the way you would expect from there. A postdoc at Freiburg. A postdoc at the International Center for Theoretical Physics in Trieste. Assistant professor at Northeastern in 2009. Queen Mary University of London from 2013, and a full professorship there from 2019. Alan Turing Fellow at the Turing Institute from 2018 to 2024. Fellow of the Network Science Society in 2020. Member of the European Academy of Sciences. Fellow of the American Physical Society in 2023, with a citation praising her seminal contributions to the statistical mechanics of simple, multi-layer, and higher-order networks. The Euler Award of the Network Science Society in 2025. 3 books, 2 of them written alone, 1 from Oxford University Press, 2 from Cambridge. Her citation count is somewhere north of 20,000. Almost none of it is in gravity. As of the middle of 2026, the gravity paper has around 30 citations. She is one of the most established scientists in her field, and, in the field she has walked into, she is essentially nobody. For 25 years, the work was all in what mathematicians call the discrete, Networks first, nodes and links, points and connections. Then simplicial complexes, which is what you get when you stop insisting that connections happen only between pairs. In a simplicial complex, three nodes can share a single relationship that is not reducible to three separate pairwise links. Four nodes can. It is a way of capturing structures where things genuinely happen in groups, rather than in couples. And it turns out that a very large number of real systems, brains, ecosystems, social groups, chemical reaction networks, are like that. Her constant subject, running under all of it, was one relationship: how structure shapes dynamics, how the shape of a system determines what happens on it, whether big hubs in a network change the way an epidemic spreads, whether topology governs synchronization. That is what she has been asking, in one form or another, since the late 1990s. And around 2024, she wanted to build something more general, a comprehensive theory of the interplay between structure and dynamics, one that uses topology and geometry, and views the whole thing through the lens of information theory, because ultimately, what you want is to describe systems by their information content. And her conviction, she has said this plainly, is that information theory on its own is not enough. It has taken us extraordinarily far. It underwrites quantum computing, machine learning, every compressed file you have ever opened. But it is blind to shape. It knows how much you do not know. It does not know the geometry of what you do not know. What is missing, in her view, across a dozen fields from brain research to artificial intelligence, is an information theory that can carry the degrees of freedom of geometry itself. She hit a wall, and the wall was mathematical. In the discrete, curvature is not well defined. That is a real and stubborn problem. Curvature is the central concept in geometry, and on a smooth surface, it is completely unambiguous. You can compute it, you can measure it. Gauss and Riemann handed us the machinery 2 centuries ago. On a network made of dots and lines with nothing in between, there is no agreed answer to what curvature even means. There are proposals. Several of them are interesting. None of them is the answer. So she was stuck, with the mathematics she needed not existing. And then she went to give a seminar. Picture the room. It is at the International Center for Theoretical Physics, in Trieste, on the Italian coast, at the top of the Adriatic. The institute was founded in 1964 by Abdus Salam, the Pakistani physicist who would win the Nobel Prize in 1979, the first Muslim laureate in the sciences, together with the Italian physicist Paolo Budinic. Salam built it for a specific reason, so that scientists from poor countries would not have to leave home permanently in order to do serious work. It hosts more than 6,000 scientific visitors a year. It is, quite literally, an institution designed to put strangers in rooms with each other and see what happens. So, a seminar room in that building, on an ordinary working day. There is a projector, there are chairs that do not match. There is the specific quality of light you get in a room, with the blinds half down so the slides are legible, and the Adriatic sitting outside the window doing nothing in particular. The audience is the audience you get at an institute like this one. A dozen or 20 people, most of whom work on something else. A few of whom are only there because the talk is at a convenient time. Some of them are from other continents. Almost none of them are network theorists. Bianconi is at the front, presenting on discrete structures, simplicial complexes, the interplay between topology and dynamics. She is not describing a triumph, she is describing a problem. She has the framework, she has the information theory, she knows what she wants the theory to do, and she explains, in front of these people, that she cannot make it work, because in the discrete world, curvature is not well defined, and curvature is the thing she needs. The talk ends, hands go up, the way they do. And someone in the audience, not a collaborator, not someone she names when she tells the story, just somebody who was in the room, asks the question that is only obvious if you are standing outside the problem. If you need curvature, why don't you do it in the continuum? Her answer, which she reports verbatim in interview, was this. She said, "No, I will never go into the continuum." I love that sentence. There is nothing hedged about it. Not, "I hadn't considered it." Not, "That's an interesting thought." Never. 25 years of work, a whole set of instincts, a belief she says she was raised on, that nature is ultimately discrete, that if quantum gravity is anything, it is probably granular at the bottom, all compressed into one flat refusal to a stranger at a seminar. And then she went home and thought about it. Because the continuum version of the theory she was trying to build turned out to have a great deal to do with gravity. And if she was going to end up there anyway, she reasoned, then why not simply take on the properly difficult problem, the one everybody has been failing at since the 1930s? There is an aside she offers at this point, delivered completely flat, which I think tells you something about the temperament involved. She says, a bit controversially, in her own words, that to understand the brain is harder than to understand quantum gravity. That is not bravado. That is somebody who has spent a career on the mathematics of complex systems, making a considered judgment about which problems have more irreducible difficulty in them. Quantum gravity is one very hard question. A brain is 100 billion of them wired together. I should be careful about the anecdote itself. It is hers, told in an interview, not a documented record. There is no transcript of that seminar, no name attached to the questioner. What is documented is everything around it. ICTP is real. Her connection to it is real. She held a postdoctoral position there, and she returned in July of 2025 to give a seminar with a rather different title from the one she gave before. That one was called Gravity from Entropy. So she went into the continuum, and the first thing she had to do, before she could compare two geometries, was find a way to build the second one, which meant rebuilding matter itself. To compare two geometries, you need two geometries, and matter, as physics normally writes it down, is not a geometry. This is a real obstacle, and it is worth being precise about why. The metric of spacetime is a particular kind of mathematical object, a rank 2 tensor, which is a thing that eats two directions and hands you back a number, and the number it hands you is essentially a distance. Matter is not like that. An electron is described by something called a spinor, and a spinor is a very different animal. It has fewer components. It transforms differently. There is no obvious way to look at a spinor and extract a distance from it. Worse, a spinor is not really native to a curved space at all. To write one down, you need a choice of local frame, a set of reference directions planted at every point, and a piece of structure, called a spin connection, to tell you how those frames relate to each other as you move around. It is scaffolding. It is scaffolding that works extremely well, but it is scaffolding, and it is bolted onto the geometry rather than growing out of it. And spinors are strange in a way that most people find genuinely unsettling the first time they meet it. Rotate a spinor through a full circle, 360 degrees, all the way around, back to where you started, and it does not come back to where it started. It comes back with a minus sign. You have to turn it twice, through 720 degrees, before it is truly itself again. This is not a mathematical curiosity. It is a measured property of electrons, and it is one of the more direct pieces of evidence that the world at small scales is not built the way our intuitions insist it is. So if your entire project is to treat matter and geometry symmetrically, to put them on the same footing and ask how different they are, then you have a problem. You cannot compare two things written in incompatible languages. Erich Kähler solved this in 1962 for entirely different reasons, and nobody in gravity paid much attention. The paper is called Der innere Differentialcalcul, the interior differential calculus, published in Rendiconti di Matematica, volume 21, and it runs to nearly 100 pages. And yes, that is the same Kähler as Kähler manifolds, the objects that string theorists spend their lives on. Most physicists know his name from a completely different context and have no idea he did this. His insight was that you can write the same physics, the same equation, the same content, using nothing but differential forms. So let me tell you what a differential form is, because the definition is much friendlier than the name. A differential form is a thing you can integrate. That is genuinely the whole idea. Different kinds of form are integrated over different kinds of region. A zero form is a scalar. It is just a number attached to each point. The way there is a temperature at every point in this room. You do not integrate a zero form over anything. You simply evaluate it where you are standing. A one form is something you integrate along a line. If you walk from one side of the room to the other and add up a quantity as you go, the thing you are adding up is a one form. A potential gradient is a one form. The work done by a force along a path is the integral of a one form. A two form is something you integrate over a surface. Think of flux, the amount of something passing through a sheet of area. The electromagnetic field, written properly, is a two form. Magnetic flux through a loop is a two form integrated over the area inside it. And Kähler's construction takes these three objects and stacks them into one. A zero form plus a one form plus a two form added together as a single mathematical entity. The technical name for the sum is a direct sum, which sounds imposing and just means keep all three side by side and treat the assembly as one thing. I want you to stop and be somewhere for a moment. Shrink down. Not to the size of a molecule, not to the size of an atom, all the way down to a single point in the room you are lying in. One location, with no extent at all, and ask what is actually there, according to this theory. You do not find particles. You do not find tiny balls. You find three things, stacked. There is a number, a single value that belongs to this point and nowhere else. The way a temperature reading belongs to a thermometer's position. It has no direction. It is just an amount, sitting here. There is a direction, something you would never detect by standing still. You can only find it by moving, by walking a small distance and adding up what you accumulate along the way. It is not a thing at the point. It is a thing about going somewhere from the point. And there is an orientation, something that only means anything if you sweep out a small surface and ask what passes through it. Not a value, not a direction, but a facing, a sense of which way a little sheet of area is turned and what flows across it. A value, a line, and a surface. That is the matter. According to this theory, described honestly, that is what the stuff you are made of actually is. And now the payoff, which is the reason any of this is in the episode at all. Those three objects, stacked together, carry exactly enough structure to build a metric. Not almost enough. Exactly enough. A scalar on its own gives you one number per point, and there is no way on earth to squeeze a rank 2 tensor out of that. But a zero form and a one form and a two form, taken together and run through the right operator, produce something with two slots that eats two directions and returns a distance. Which is to say, a geometry. A second answer to how far apart things are, constructed purely out of what is present, rather than measured off the manifold. The operator that does the work is called the Hodge-Dirac operator, and it has an elegance I cannot resist mentioning. It is built from the exterior derivative, and its adjoint, two operations that already exist on any manifold, requiring no extra structure whatsoever. And when you square it, you get the Laplacian, which is exactly the relationship the ordinary Dirac operator has with the wave operator. Kähler's version does the same job with none of the scaffolding. And here is where it stops being a coincidence that a network theorist wrote this paper. The Hodge-Dirac operator is not something Bianconi picked up when she started thinking about gravity. It is something she had already been using for years, on discrete structures, in a completely different context. One of her network papers is called Dirac Signal Processing of Higher-Order Topological Signals. It applies this same operator to data living on simplicial complexes, to signals that sit on the edges and faces of a network rather than on its nodes. She had spent years with the exact mathematical machinery that turns out to be what you need to describe matter without a frame. She did not learn it for gravity, she brought it with her. There is an ancestor to all this, and it is 200 years old. Carl Friedrich Gauss's first fundamental form. Take a surface. Define a function on it. Picture that function as a height, so the function traces out a shape above the original surface. Gauss showed that this shape inherits a metric from the function that defines it, a geometry induced by content. Bianconi's construction is that idea, extended from a single scalar to the full stack. This is not an antique, either. The Dirac-Kähler formalism is currently live in lattice gauge theory, where it connects to something called staggered fermions, the standard computational workhorse used to simulate the strong nuclear force on supercomputers. The connecting paper is Becker and Jose, 1982. Bianconi also cites recent work extending the formalism to bosonic particles. And now the caveat, which I am going to say plainly, rather than let you discover it later. The published continuum theory treats bosonic matter fields. Her own words in the paper. In the main body of this paper, we will investigate only bosonic Dirac-Kähler matter fields. However, gauge fields and fermionic Dirac fields can be included as well. Abelian gauge fields are sketched in an appendix. Fermions and non-abelian gauge fields are left to future work. Fermions are the matter you are made of. Electrons are fermions. Protons and neutrons are made of quarks, and quarks are fermions. Every atom in your body is held together and given its bulk by particles this version of the theory does not yet contain. Bianconi says, the goal she is working toward is a formulation where you can put the whole standard model in. That is a statement of intent, not a result. As published, in the continuum, the theory does not contain electrons, which is why it is a proposal and not yet a description of the world, and why the thing to judge it on is not whether it is finished, but whether the idea inside it is worth finishing. Because we now have both geometries, and the whole theory is what happens when you put them side by side. Both objects now exist. On one side, the true metric of space-time, the ordinary metric of general relativity, the thing that defines the Ricci scalar and the Riemann curvature tensor, and tells you the distance between two nearby events, whatever it is, no assumption about its shape. On the other side, the metric induced by the matter fields and curvature, the second geometry, built out of a value, a line, and a surface, plus what the curvature is doing at that point. You have two descriptions of the same location, and two answers to the same question. And Bianconi's proposal is that the Lagrangian of gravity, the quantity you integrate to get the action, the thing nature is extremizing, is the geometric quantum relative entropy between them. Let me unpack what that actually means physically, because the phrase is forbidding and the content is not. Relative entropy, as we established, is a measure of surprise. It asks, given that I hold description A, how surprised should I be by description B? How much information in one is already codified in the other? So the Lagrangian of gravity, in this theory, is a measurement of how surprised the geometry should be by the matter. Or, put the other way around, and Bianconi's own framing of the tension is the clearest version I have found. It is as though the matter field is telling the metric what it would like the true metric to be, and the true metric is telling the matter field how to move. Both statements, simultaneously, encoded in one expression. And because relative entropy is minimized when two descriptions agree, the whole system is under a permanent tension. The two metrics are straining toward each other. They want to be the same thing. They never get there. It is worth saying what the second metric is actually made of, because the recipe is simpler than you might fear. Take the true metric. Add a term carrying the matter fields, the value, the line, and the surface from the last part. Subtract a term carrying the curvature. That is it. Two corrections to the true geometry, one from what is present, and one from how bent things are, each multiplied by a coupling constant. And those coupling constants are not arbitrary numbers. They are set by powers of the Planck length, the scale at which space-time is expected to stop behaving classically, about 1.6 times 10 to the minus 35 meters. One coupling carries the Planck length to the fourth power. The other carries it squared, which means the two geometries agree almost perfectly at any scale you or I will ever encounter, and diverge only when you get down into the region where physics is expected to break anyway. The disagreement is real everywhere. It is simply, at human scales, extraordinarily small, and it is precisely that smallness that lets the theory reproduce Einstein. There is also a lineage note that matters. Bianconi writes in the paper that the quantum relative entropy proposed in the work is strictly related to the Araki quantum relative entropy for von Neumann algebras. That is not a decorative citation. It is the reason the object is finite. Everything from the last part, the modular operator, the cancelling divergences, the reason a bare entanglement entropy is unusable, is what allows this Lagrangian to be written down without immediately producing an infinity. Now, there is an objection you should be raising at this point, and it is exactly the objection an interviewer put to her directly. It sounds like you are putting Einstein's equations in at the start in order to get Einstein's equations out at the end. If you already know that matter tells space-time how to curve, and you build an action designed around that relationship, of course you will recover the field equations. That is not a derivation. That is a restatement. Her answer is unambiguous. There is no assumption of any Minkowski background. Absolutely not. The true metric is the true metric, the one that defines the Ricci scalar and the Riemann curvature, on a general Lorentzian manifold, whatever shape it happens to have. Flat space is nowhere in the construction. And the second metric is not Einstein's. It is a geometrization of the matter, built from Gauss's first fundamental form and the Dirac-Kähler stack, using mathematics that has nothing to do with gravity at all. What she puts in is, here are two geometries, and here is how you measure the difference between two quantum states. What comes out is gravity. There is one mathematical fact that makes the whole thing hang together, and it is elementary enough that anyone can appreciate it. The trace of a logarithm is the logarithm of a determinant. That sounds like a technicality. It is the load-bearing wall. Because a relative entropy is written as the trace of a logarithm, and the logarithm of a determinant is, structurally, a count, a logarithm of a number of configurations, which means the same expression can be read two completely different ways at the same time. Read it one way, it is a comparison between two quantum states. How surprised should you be? Read it the other way, it is Boltzmann counting microstates. How many arrangements are consistent with this? It is a relative entropy and a Boltzmann entropy simultaneously. I find this genuinely remarkable, and I think it is the most important feature of the theory. Everything we spent the first hour building, the counting entropy from Vienna and the comparing entropy from Kyoto, turns out to be two readings of one quantity. Bianconi makes this explicit in the follow-up work, writing the Lagrangian as the logarithm of a number of configurations and calling it a Gibbs-Maxwell entropy of the geometric degrees of freedom of spacetime. Now let me put the theory next to Einstein's, because the comparison is the whole point. John Wheeler gave physics the sentence everyone quotes, "Matter tells spacetime how to curve, and space-time tells matter how to move. It is beautiful, it is memorable, and it is on the first page of every popular treatment of general relativity ever written. Here is what almost nobody mentions. That two-way conversation exists in Einstein's field equations. It does not exist in the action those equations come from. The Einstein-Hilbert action, plus matter, is not symmetric at all. Geometry gets its own term, the curvature scalar, integrated over spacetime. Matter gets its own term, whatever the matter Lagrangian happens to be. And then the two are joined by something called minimal coupling, which is a technical way of saying, put them next to each other and let the geometry appear in the matter term where it has to. There is no symmetric treatment. There is no comparison. There are two separate things stapled together in a way that happens to produce, when you vary it, equations that describe a conversation. Wheeler's sentence is a description of the answer. It was never a description of the question. In Gravity from Entropy, it is in the question. Both sides are metrics. The action is a comparison between them. The symmetry is exact, not approximate, not aesthetic, structural. Matter and geometry enter the action in precisely the same way and are interpreted in the light of their mutual information content. So what comes out? Vary the action, and you get modified Einstein equations. And in the regime of low coupling and small curvature, which is to say every regime in which general relativity has ever been tested, every orbit, every clock, every gravitational wave detection, those equations reduce to the ordinary Einstein equations with zero cosmological constant. Everything Einstein got right, this gets right. Two technical properties are worth naming, because they are not automatic, and they are the reason serious people have taken the theory seriously. First, the equations of motion remain second order, in the metric and in the extra field we will meet shortly. This matters more than it sounds. Modified gravity theories generically produce equations with higher derivatives, and higher derivatives generically produce ghosts, degrees of freedom with negative energy that make the whole thing unstable and unphysical. Staying second order is a real structural virtue, and Bianconi flags it as one. Second, and much stranger, the theory produces corrections at the Planck scale, even in flat, empty geometry, because the action depends on the entire Riemann curvature tensor, not just on the Ricci scalar or the Ricci tensor, but on every component, including the parts that carry no trace at all. It does not vanish in empty space. The Ricci scalar can be zero, and the action is still non-zero. There is a Planck scale correction sitting in the vacuum of flat spacetime in this theory. That will matter enormously in about 20 minutes. But I want to slow down here, because there is something underneath all the machinery that I think is the actual point of this episode. If this is right, gravity is not a force. It is also not, quite, what Einstein said it was. Einstein said, gravity is geometry, that things fall because space-time is curved, and they are simply following the straightest available path through a bent landscape. That picture is not overturned here. It survives completely, but it is reframed. Because in this picture, the curvature itself is not the fundamental thing. The curvature is what you get when two descriptions of the same place fail to agree, and the failure has to go somewhere. Every object you have ever dropped in your life fell because of that. Every stumble, every time you sat down and the chair held you, every time you climbed stairs and felt it in your legs, every time you have lain in bed and been quietly, invisibly pressed into the mattress by something you have never once seen. It was not something acting on you. It was something not quite agreeing with itself and you living inside the gap. That is the idea. Not frightening. I do not think there is anything frightening in it. But it does mean that the most familiar experience any of us has, the one every single human being has had every second of their life, is the visible edge of an argument that has been running since there was anything to have an argument about. Let that settle for a moment. The room, the mattress, the completely uneventful fact of weight. And notice that we still have not answered the question we started with. We have a beautiful rewriting. We have symmetry where there was none, a finite quantity where there were infinities, and a theory that reduces correctly to everything we have tested. That is not the same as a new origin for gravity. An elegant reformulation is a very long way from a discovery. We are not ready. We are about halfway through, and this is a good place to stop climbing for a few minutes and look back down at the ground we have covered. If you have been drifting, and there is no reason you should not be, that is what this channel is for. This is where you can pick the thread back up without having missed anything. There are 6 things. That is all we have established, and every one of them is simple on its own. The first is this. Entropy is not disorder. Entropy is a measure of how much you do not know about a system, given what you do know about it. Boltzmann worked that out in the 1870s, and it cost him a great deal. The equation on his gravestone was written by somebody else. The constant in it was frozen to an exact decimal by International Committee in 2019. Ignorance, quantified. That is the whole of it. The second is this. There is another quantity in the same family that does something different. It does not count. It compares. Relative entropy takes 2 descriptions of the same thing and asks how surprised you should be by the second, given that you held the first. 0 when they match. Large when you were badly wrong. Kullback and Liebler gave it to mathematics in 1951. Umegaki carried it into the quantum world in 1962, and Araki rescued it for quantum field theory in 1976. The third is the one that makes everything else possible. The ordinary entropy of a region of empty space in quantum field theory is infinite. You have to cut it off by hand, and the answer depends on where you cut. The relative entropy between 2 states of that same region is finite, because both carry the same divergence, and it cancels exactly when you compare them. 2 infinities of the same shape, subtracting cleanly. That is not a nicety. That is the reason this theory can be written down at all. The fourth is this. Matter can be described without any of the usual scaffolding. No frames, no coordinates, no spin connections. Just a value at a point, a line you can walk along, and a surface you can measure a flow through. Kähler worked that out in 1962, for reasons that had nothing to do with any of this. The fifth is this. That stack, the value, the line, and the surface, carries exactly enough structure to build a geometry out of. Not measure one, build one, which means that at every point in this room, there are now 2 answers to the question of how far apart things are, the true geometry and the one you would reconstruct from the contents. And the 6th is this. They do not agree. And the proposal is that the disagreement is gravity, that the action of the universe is a measurement of how much those 2 descriptions differ, and that everything falling is nature straining to close a gap it cannot close. That is the first half of tonight. Take a moment with it before we go on. There is no hurry, and nothing in the next few sentences requires you to be paying close attention. Think of the room you are in as a photograph that has been printed twice, from 2 different negatives, and laid one on top of the other. Almost every line matches. The edges of the walls sit where the edges of the walls sit. The corners meet. If you looked at it casually, you would never notice there were 2 images there at all, and at the scale of a room, or a planet, or a galaxy, the offset between them is smaller than any instrument has ever measured, smaller by a factor with dozens of zeros in it. But the 2 prints are not the same print. Somewhere, far below anything anyone can see, the lines are fractionally out of register, and according to this theory, that faint, universal, unresolvable misalignment is what everything in the universe has been falling toward for 13.8 billion years. Now, here is the thing I want you to notice about all of it. Nothing I have described so far is a discovery. Everything up to this point is a rewriting, a very beautiful rewriting, with a symmetry that Einstein's version does not have, and a finite quantity where other approaches produce infinities, but a rewriting nonetheless. It reproduces general relativity in every regime we have ever tested. That is a requirement, not an achievement. Any theory that failed to do it would have been dead on arrival. Physics is absolutely full of elegant reformulations. There are at least 4 different ways to write down classical mechanics, and they all say exactly the same thing. You can write electromagnetism as 4 vector equations, or as 2, or as 1, depending on how much machinery you are willing to carry. None of those reformulations told anyone anything new about the world. They made things easier to see. That is valuable, and it is not the same as discovery. So the honest question, at the halfway mark, is this. Is that all this is? A more symmetric way to write down something we already knew. And I want to be fair to reformulations while I say that, because they are not nothing. The reason there are 4 ways to write classical mechanics is that each one makes a different class of problem easy. Newton's version is the one you want for a cannonball. Lagrange's version is the one you want for a pendulum hanging off another pendulum. Hamilton's version is the one that turned out, a century later, to be the doorway into quantum mechanics, which nobody could possibly have known at the time, and which is precisely why you keep the reformulations around. Sometimes the new way of writing something is a new way of thinking about it in disguise, and you only find out decades later. But that is a hope, not an argument, and hope is not evidence. There is a test, and it is the only test that has ever mattered in this business. Does the theory tell you something you did not put in? That is the whole distinction between passing an exam and saying something new. Anyone can build a framework that reproduces the answers they already know. You simply keep adjusting it until it does. The question is whether, once you stop adjusting, the framework hands you back something you were not expecting and did not ask for, something that falls out of the mathematics on its own, that you would then have to go and look for in the sky. Newton's theory did that. He built it to explain the orbits of the planets, and it handed him back the tides, and the shape of the Earth, and the return of a comet in 76 years. Einstein's did it. He built it to reconcile gravity with special relativity, and it handed him back the bending of starlight, the drift of Mercury's orbit, black holes, and an expanding universe he initially refused to believe in. So, does gravity from entropy hand anything back? It does. There is something in this theory that Bianconi did not put in, that appears when you rewrite the action in the right variables, that has the right sign, that has roughly the right size, for a reason built into the structure of the mathematics, and that happens to be the single most embarrassing number in all of theoretical physics. She did not go looking for it. It was simply there when the algebra settled. And I should be clear about the standard it has to meet, because a theory producing an extra term is not automatically impressive. Modified gravity theories produce extra terms constantly. That is more or less what they are for. What matters is whether the extra term has properties the author could not have chosen, whether its sign, its size, and its behavior are dictated by the structure rather than by the person doing the writing. Hold that criterion in your head for the next 20 minutes. Sign, size, behavior. Not chosen. Let us go and meet it. To get at what falls out, Bianconi has to do a piece of mathematical housekeeping, and the housekeeping turns out to be the most interesting part of the paper. When you have an action with constraints in it, conditions that have to be satisfied, there is a standard technique for handling them, invented by Joseph Louis Lagrange in the 18th century. You introduce extra quantities called Lagrange multipliers, one for each constraint. They are bookkeeping devices. You put them in, you turn the crank, and at the end they usually drop out again, having done their job. Bianconi introduces a set of them to enforce constraints on the metric induced by the matter fields. She calls the resulting object the G field. Now here is the thing about Lagrange multipliers that most people are never told, and that anyone who has worked in statistical mechanics knows in their bones. Sometimes they are real. The cleanest example is one you rely on every day. When you derive the distribution of energies in a gas, you maximize the entropy subject to the constraint that the total energy is fixed, and to handle that constraint, you introduce a Lagrange multiplier. It goes in as pure bookkeeping, with no physical meaning at the point you write it down. That multiplier is temperature. The most familiar physical quantity in the world enters the mathematics as a formal device, and then turns out to be a real, measurable property of matter. So when Bianconi says the G field is a Lagrange multiplier and she would like to give it a physical meaning, she is not overreaching. She is pointing at the most successful precedent in the subject. And when you rewrite the action in terms of the G field, something structural happens. The single relative entropy expression splits into three recognizable pieces. The first piece looks very close to the Einstein-Hilbert action, the thing Einstein and Hilbert wrote down in 1915, but with a difference. The curvature scalar in it is dressed. What that means is that the metric appearing there is not quite the true metric. It is the true metric contracted with the G field. So what actually interacts with matter, in this theory, is not the bare geometry, it is the geometry wearing a coat. The second piece is the matter action, also dressed, coming from the geometry induced by the matter fields and the curvature. And the third piece is a cosmological constant. Nobody asked for it. It is not a parameter she chose. It is not tuned. It is what is left over when you rewrite the action honestly. And it depends on nothing but the G field. Let me tell you why that is a big deal. And to do that, I have to tell you about the worst prediction in the history of physics. Quantum field theory says empty space is not empty. Fields fluctuate. Even with nothing in it, the vacuum carries an energy density, and general relativity says any energy density gravitates. So you can calculate what the vacuum energy of the universe ought to be, and then you can go and measure what it actually is, and compare. The two numbers do not match. How badly they fail to match depends entirely on where you decide your theory stops applying. If you assume quantum field theory holds all the way down to the Planck scale, the calculated value exceeds the observed value by something like 120 orders of magnitude. That is a 1, followed by 120 zeros. It is routinely described as the worst quantitative prediction ever made by a successful scientific theory, and that description is fair. But if you are more careful, if you cut the calculation off at the electroweak scale instead, or handle Lorentz invariance properly rather than naively, the mismatch comes down to something nearer 60 orders of magnitude. Still catastrophic, but a different number. The honest thing to say is that estimates range from about 60 to about 120 orders of magnitude, depending on your assumptions, and that the spread itself tells you how much of that famous figure is physics and how much is bookkeeping. So what is the actual value? What is the number that theory cannot reproduce? According to the Planck satellite results of 2018, dark energy accounts for about 69% of the total energy density of the universe. Cold dark matter is about 27%. Ordinary matter, stars, planets, gas, dust, is about 5%. 69% sounds enormous. In absolute terms, it is nothing at all. The critical density of the universe is about 9 times 10 to the minus 27 kilograms per cubic meter, which, in the astronomer Barbara Ryden's comparison, is equivalent to taking the matter in one small drop of water and spreading it evenly over the entire volume of the Earth. Dark energy is about 2/3 of that, which in energy terms is roughly 6/10 billionths of a joule per cubic meter. That is 6/10 billionths of a joule per cubic meter. The energy in a single AA battery, spread across about a cubic kilometer. That is the number driving the accelerating expansion of everything. That is the number that will, in the end, determine whether the universe carries on expanding forever and empties itself out. And it is the number that quantum field theory misses by a factor with 60 zeros in it. Now, in gravity from entropy, that constant is not chosen, and it has three properties that Bianconi did not select. It depends exclusively on the G field. Nothing else enters. It is strictly non-negative. It cannot come out with the wrong sign. This matters more than it might sound, because a great many otherwise attractive theories, string theory in its more tractable versions among them, have a persistent difficulty producing a positive cosmological constant. They keep wanting to give you a negative one, describing a universe that contracts rather than accelerating outward. Ours accelerates. Bianconi's theory can only give you the kind we actually live in. And it is small for a reason built into the structure. When the G field sits near the identity, when the two geometries are nearly in agreement, which at ordinary scales they are, the first non-trivial contribution to this term is quadratic. The deviation is squared before it ever reaches the equations. A small disagreement produces a very much smaller constant, automatically, without anyone tuning anything. Sign, size, and behavior are all fixed by the structure. None of them was chosen. I want to be careful not to oversell this. Producing a small positive number is not the same as producing the right small positive number. And nobody has demonstrated that the value this theory gives matches the value the sky gives. That calculation has not been done. But in a field where the standard outcome is being wrong by 60 orders of magnitude, a theory that produces a small positive dynamical constant as a consequence, rather than an input, has done something genuinely unusual. And there is one more property, which turns out to be the most topical of all. It is dynamical. It is not frozen at a single value for all time. It varies as the universe evolves, because the G field varies. Which brings us to what the telescopes have been finding. The Dark Energy Spectroscopic Instrument, DESI, is a survey that has now measured the positions of more than 14 million galaxies and quasars. Its second data release, in 2025, reported something that has unsettled cosmology considerably. Under the standard model, with dark energy as a fixed, unchanging constant, DESI's measurements sit in mild tension with the cosmic microwave background, about 2.3 sigma, not fatal, uncomfortable. Allow the dark energy to evolve, to have an equation of state that changes with time, and the tension eases. The collaboration's own words are that the tension is alleviated by dark energy with a time-evolving equation of state. The preference for evolving dark energy over a fixed constant runs at 3.1 sigma when you combine DESI with the microwave background, and between 2.8 and 4.2 sigma when you add supernovae, depending on which supernova sample you use. And the direction of travel matters. In the first data release, in 2024, the figure was 3.9 sigma. In the second, with more data, it went to 4.2. Evidence that strengthens as data accumulates is the kind you take seriously. Evidence that weakens is usually a statistical fluctuation dying quietly. There is a stranger detail worth a minute of your time. DESI's data also constrains the total mass of the neutrinos, and under the standard fixed constant model, it pushes that mass toward values that are physically impossible, negative. It runs about 3 sigma against the laboratory lower bound, which is around 0.059 electron volts, and is not in serious doubt. Allow dark energy to evolve, and that problem disappears too. 2 apparently unrelated anomalies, dissolving under one and the same fix, is exactly the sort of thing that makes theorists sit up. The collaboration's closing line in the cosmology paper is unusually direct for a large collaboration, unless there is an unknown systematic error associated with one or more datasets. It is clear that the standard model is being challenged, and that dynamical dark energy offers a possible solution. So here is a theory whose author was not thinking about cosmology, which produces a dynamical dark energy term as a structural consequence, arriving in the same 18 months that 14 million galaxies started pointing toward dynamical dark energy. And now I have to give you the other side of it, because this is where a lot of coverage of this story goes wrong. There is a second great anomaly in cosmology, called the Hubble tension, and Bianconi's theory has been widely associated with it, largely because her own university press release raised the possibility. Here are the numbers. Measure the expansion rate of the universe from the cosmic microwave background, running it through the standard model, and you get 67.4 kilometers per second per megaparsec, plus or minus 0.5. Measure it directly and locally, using supernovae calibrated against Cepheid variable stars, and you get 73.04, plus or minus 1.04. Those two numbers disagree by about 9%, at better than 5 sigma, and the gap has not closed in a decade. The local measurement is not sloppy work. It is built from 42 Type 1a supernovae in 37 host galaxies, calibrated against Cepheids, which are themselves calibrated against 4 independent geometric anchors, parallax from the Gaia spacecraft, eclipsing binary stars in both Magellanic Clouds, and the Megamaser galaxy, NGC 4258. And you cannot blame the microwave background either. Bypass it entirely, using DESI's own measurements with Big Bang nucleosynthesis, and you get 68.53, still 3.5 sigma from the local value, and completely independent of Planck. James Webb has now remeasured 19 of the 37 calibrating galaxies and excluded the most popular explanation, that the Cepheid measurements were contaminated by crowded neighboring stars at 8 sigma. The summary from Vivian Poulin, writing in CERN Courier in March of 2025. At this stage, no single systematic error seems likely to fully explain the Hubble tension. So, could a dynamical cosmological constant fix it? Here is the honest answer. Nobody knows, and nobody has checked. There is no published paper fitting gravity from entropy against Hubble constant data, not one. The observation that the theory produces a time-varying constant is a structural fact about the theory. It is not a demonstration that this particular time-varying constant closes that particular gap. And it is worse than merely unchecked. The published expert view runs the other way. Poulin, in the same article, points out that supernovae and baryon acoustic oscillations together constrain the entire history of expansion out to a redshift of about 1, which severely limits what you are allowed to change in the late universe. And then, directly, recent DESI results suggest the dynamics of dark energy at late times may not be exactly that of a cosmological constant, but the behavior needed to reconcile the early and local measurements is strongly excluded. The favored direction among the people who work on this problem full-time is not late-time dark energy at all. It is early universe physics, something that shortens the sound horizon by about 10 megaparsecs before recombination, like extra relativistic particles, or a burst of early dark energy. So the correct posture is this. The theory predicts a dark energy that changes with time. That is the same family of answer DESI is pointing toward, which is genuinely interesting. Whether this specific one helps with the Hubble tension, nobody has calculated, and there is a serious published argument that the whole category is the wrong place to look. That is less satisfying than a clean claim. It is also what live science actually looks like from the inside, and it is not going to age badly. We still are not ready to answer the question, but we are closer, and there is one more thing this theory does that nobody expected. and it happens somewhere much darker. Everyone we met earlier put the entropy on a surface. Bianconi does not, and the reason she gets away with it is the most quietly satisfying result in the whole paper. Let me first lay out the standard argument properly, because it is genuinely good, and it has convinced a lot of very clever people for 50 years. Bekenstein tells us a black hole's entropy is proportional to the area of its horizon. That is peculiar. Entropy normally scales with volume. Double the size of a box of gas, and you double the number of molecules, and therefore, roughly, double the entropy. Everything works that way. Except black holes, where doubling the radius multiplies the volume by 8, but the entropy only by 4. So the reasoning goes, if the entropy scales with area rather than volume, then the degrees of freedom being counted cannot be spread through the interior. They must live on the surface. And from that observation grows the holographic principle, the idea that everything happening inside a region is somehow encoded on its boundary, that the universe is in some fundamental sense a projection. It is a beautiful argument. It has produced enormous amounts of good physics. And Bianconi's response is to point at an assumption buried inside it that nobody usually says out loud. The argument assumes the degrees of freedom are distributed uniformly inside the black hole. That is the hidden premise. If the interior has the same density of whatever you are counting everywhere, then integrating that density over a volume must give you something that scales like volume. There is no way around it. So the only escape is to move everything to the surface. But if the interior is not uniform, the argument does not run. And in gravity from entropy, the interior is emphatically not uniform. Here is why. The Lagrangian depends on the full Riemann curvature tensor. Every component of it, including the parts that carry no trace and vanish from the Ricci scalar entirely. Those trace-free components have their own name, the Weyl curvature. Weyl curvature is what is left of gravity when you take all the matter away. It is the part of the field that propagates, the part that carries gravitational waves, the part that is non-zero in a perfect vacuum, which means the density of geometric degrees of freedom in this theory varies with how far you are from the center. Fall inward. Do not hurry it. Nothing here needs to be dramatic. Just drift down through the horizon of a black hole and pay attention to something nobody usually mentions. In the standard picture, there is nothing to notice. The interior of a Schwarzschild black hole is featureless. There is vacuum, and more vacuum, and the tidal forces climb, and eventually there is the singularity. The uniformity is exactly why the entropy had to be pushed out onto the horizon. There was nothing in here to count. In this theory there is. As you descend, the density of geometric degrees of freedom changes. Not because there is matter here, there is no matter here, but because the shape of the emptiness is different at different depths, and the quantity being counted is sensitive to the whole of that shape, rather than just its average. There is more of something at this depth than at that one. The falling is not uniform. Picture it as a fog that is not evenly thick. Near the horizon, it has one density. Further down, it has another. It is not that anything is in here with you, nothing is in here with you, but the emptiness has texture, and the texture is a function of depth, and the theory is counting the texture. And when you add it all up, when you integrate that varying density through the entire interior volume, out to the Schwarzschild radius, the total does not scale with the volume you integrated over. It scales with the area of the horizon you fell through. For a black hole with the mass of the Sun, that is about 4 times 10 to the 77th, roughly 20 orders of magnitude more than the entropy of the whole Sun, packed into a horizon whose area is comparable to that of a large city. You get area out of volume, with no surface put in anywhere. You have seen this trick before tonight, in a different costume. In quantum field theory, the entanglement entropy of a region runs away to infinity. And the relative entropy between two states of that region is finite, because the divergences are identical and cancel. Two infinities of the same shape, subtracting cleanly. Here, a quantity that ought to grow with volume collapses onto a surface, because what is being counted is a difference rather than a total, and differences do not behave the way totals do. That is the same move. Nature is not counting how much there is. Nature is counting how much things fail to match, and quantities of that kind have a habit of being smaller and better behaved than anyone expects. There is a further step in the follow-up work that turns this from a nice result into a piece of machinery. Bianconi imposes the area law. She demands that the Schwarzschild entropy come out as area over 4G for large black holes, and that single requirement fixes the coupling constants of the entire theory. Two free parameters, pinned by one condition. And then she immediately hedges her own result. The derivation relies on a Wick rotation of the time coordinate, a standard but not entirely innocent mathematical maneuver. So, in her words, she takes a conservative approach and expresses the thermodynamic properties as functions of the coupling rather than treating the numbers as settled. I want to note that, because it is a good sign. A scientist who has just derived a famous result from her own theory, and who then declines to bank it because of a technical worry in the middle of the derivation, is a scientist worth listening to. Her considered position on holography, put to her directly, is more nuanced than a rejection. She thinks the area law is fundamental. She thinks there are many important insights that came from it, but she thinks it is a macroscopic law, a statement about bulk behavior, in the same category as the laws of thermodynamics before Boltzmann, and that if you are looking for a fundamental theory, you have to go underneath it. For the moment, she says, she does not feel the need to use a holographic screen. That is the distinction we set up an hour ago, returning with teeth. Thermodynamics tells you the rule. Statistical mechanics tells you why. And the follow-up paper, Thermodynamics of the Gravity from Entropy Theory, published in Physical Review D, Volume 114, Article 02-4042, in 2026, takes that seriously enough to build a whole thermodynamics out of it. The results are strange in a way I find genuinely hard to shake off. For a homogeneous, isotropic, expanding universe of the kind we actually live in, the theory's Lagrangian collapses into 5 distinct pieces, and every one of those pieces has its own temperature and its own pressure. Bianconi calls them K temperatures and K pressures, and they satisfy a first law of thermodynamics of exactly the classical form. A change in energy equals a temperature times a change in entropy minus a pressure times a change in volume. Read that again, with attention to what has a temperature. It is not the matter, it is not the radiation, it is not the quantum fields living on space-time. It is space-time, the geometry itself, at every point, locally hot and locally under pressure, with values that evolve as the universe expands. In the low-energy regime, the temperature falls off as 1 over time squared, and the pressure as 1 over time to the 4th. The empty space in the room you are lying in has a temperature in this theory, not the air, the geometry, a quantity you could in principle measure and that no instrument ever built comes remotely close to detecting. And then there is the result that produced the headlines, which I want to state in the paper's own careful language rather than the popular version. The paper says, the total relative entropy per unit volume is not increasing, consistent with its nature as a relative entropy, while the total entropy of these universes is not decreasing in time. Those two words are non-increasing and non-decreasing. That is weaker than the press summary, which rendered it as entropy per unit volume going down while total entropy goes up. But the implication survives, and it is remarkable. The same quantity, read locally, is a relative entropy that is shrinking. Read globally, it is a total entropy that is growing. which dissolves an old and genuinely irritating tension. People have asked for a century how it is that the universe obeys the second law, everything running down, entropy always climbing, while simultaneously producing galaxies and stars and planets, and eventually, us, structure appearing in a universe supposedly sliding into uniformity. In this picture there is no conflict, because the second law and the emergence of structure are two readings of one number. Let that sit for a moment. The expansion of everything, the steady, patient increase in the total, and inside it, locally, in every cubic meter, two descriptions of the same place, quietly moving closer together. A theory is not what its author says about it. A theory is what happens when other people take it somewhere its author never went. 18 months have passed since publication, and 3 groups on 3 continents have done exactly that. This is the scoreboard, and I am going to give you all of it, including the entry that may sink the whole thing. The first push came in September of 2025 from Yangzhou University in China. Uday Krishna Thatarampilli and Yunlong Zheng at the Center for Gravitation and Cosmology took the gravity from entropy field equations and asked what they do in the very early universe. The paper is called Inflation from Entropy, and it was published in the European physical journal C. What they found is that the vacuum equations admit inflationary solutions. Let me make sure that lands, because it is easy to let it slide past. Cosmic inflation is the standard account of the first fraction of a second after the Big Bang, a period of almost unimaginably rapid expansion that explains why the universe is as smooth and as flat as it is. The evidence for something like it is strong, but the standard mechanism requires a field, called the inflaton, that drives the expansion. Nobody has ever detected an inflaton. Nobody knows what it is made of. Its potential, the shape of the energy landscape it rolls down, is not derived from anything. It is chosen, by hand, to produce the results we observe. There are hundreds of proposed versions in the literature, and no way to pick between them. In the Yangzhou calculation, no inflaton is added. The inflationary behavior comes out of the vacuum equations of the theory. The empty space equations, on their own, want to inflate. There is a caveat, and they state it. The prediction of a viable spectrum assumes that the usual relationship between the slow roll parameters and what we measure in the microwave background carries over unchanged into entropic gravity. That is an assumption, not a proof. And the equations also admit a regime of phantom-like behavior, which is a technical way of saying they can also do things that look unphysical if you push them too far. But inflation without an inflaton, from equations written down for a completely unrelated reason, is exactly the kind of thing you hope for when a new theory arrives. The second push came in February of 2026, from the same Yangzhou group, joined by Vishnu Kakat, with affiliations in Sweden and South Africa. Their paper, Spherically Symmetric Black Holes in Gravity from Entropy and Spontaneous Emission, appeared in Physical Review D, Volume 113, Article 104002. They thank Bianconi in the acknowledgements for her insights. They asked what a black hole looks like in this theory, and the answers are unusual. Start with the geometry. The classical Schwarzschild solution picks up corrections that fall off as 1 over the radius to the 4th power, very steep, meaning they are utterly negligible far away and become significant only close in. Second, the horizon moves. In this theory, the event horizon does not sit at the Schwarzschild radius. It sits slightly outside it, at the Schwarzschild radius, plus a correction, and the correction grows relatively larger as the black hole gets smaller. Third, there is a real observational constraint. The Event Horizon Telescope's image of Sagittarius A star, the black hole at the center of our galaxy, gives a shadow with an angular diameter of 51.8 microarc seconds, plus or minus 2.3, for an object of about 4.15 million solar masses at a distance of about 8,178 parsecs. Feeding that in, the authors extract a 2 sigma bound on the theory's coupling constant. It is a broad bound, the theory is nowhere near ruled out, but it is a number, from a photograph, constraining a theory of quantum gravity. That is rarer than it should be. They also check the orbit of the star S2, which loops around Sagittarius A star every 16 years, and whose relativistic precession has been measured by the gravity collaboration to a precession factor of 1.10, plus or minus 0.19. That test turns out to be far weaker. The theory sits comfortably inside the bounds across the whole range they examined. The shadow is the sharper instrument. Now hover for a moment, just outside such a black hole, in the version of reality this theory describes, and compare it with the one you know. The horizon is in the wrong place, not dramatically, fractionally further out than Einstein says, by an amount that grows as the object shrinks. And there is something else, which is much stranger. In the ordinary picture, a black hole this large is essentially eternal. Hawking radiation exists, but for anything of stellar mass, the evaporation timescale is a number so large that calling it astronomical is an insult to astronomy. These objects outlive every star that will ever form. In this calculation, that is not what happens. There is a background evaporation rate that does not depend on the mass at all, a constant leak. The authors describe it as the black hole leaking energy into the entropic fabric of spacetime at a steady rate, regardless of its size. Think about that. The largest object in a galaxy, and a small stellar mass one, draining at the same steady pace. Not radiating in the Hawking sense. There are no quantum fields on a fixed background here. No particle creation at the horizon. This is a purely classical response of the modified geometry. The vacuum in this theory is not stationary. It has an underlying dissipative flow, and everything sits in it, seeping. Your whole relationship with black holes is built on permanence, the thing that takes and does not give back. Here, even that is quietly draining, forever, into something nobody can name. At intermediate scales, the framework does reproduce the standard Hawking mass loss behavior, but again, classically, from the modified background rather than from quantum field theory, and the effective temperature that comes out scales as 1 over the square root of the mass, rather than 1 over the mass, as in Hawking's result. Macroscopic black holes in this theory are warmer than in general relativity. The heat capacity stays negative, so they remain thermodynamically unstable, exactly as before. Now the two problems, because there are two, and I am not going to bury them. The authors flag the first themselves. In their solution, the product of the two metric functions is no longer equal to 1. That sounds like a technicality. It is not. It means the solution violates the strong equivalence principle, one of the foundational assumptions underneath general relativity, the statement that the laws of physics are the same in every freely falling frame. A theory that violates it is not automatically dead, but it has a great deal of explaining to do. The second problem is the one I most want to correct, because the hopeful version of it is already circulating. Bianconi has speculated, carefully, as speculation, that the singularity might be avoided in this theory. Her reasoning is sound. The G-field is dynamical, and close to where the singularity would be, it becomes strongly dynamical, so there may be no single static black hole solution at all, and the infinity might simply not form. Somebody finally did the calculation. The singularity is still there. Their sentence, plainly, except at the origin, all the singularities are removable. The curvature invariant still diverges as you approach the center. What the corrections do is move the horizon. They do not heal the core. There is one hopeful line in the conclusions, and it is explicitly conditional. If the equations lead to a vanishing mass loss rate at some finite non-zero mass, then the theory would naturally predict stable black hole remnants, and that would make it a serious candidate for a theory that avoids naked singularities. If. As of now, an open if. And then there is the third push, from July of 2026, and it is not a friendly one. David Pereira posted a 26-page paper called Vacuum Gravity from Entropy, Stability, Spectra, and Exact Waves. It is the first serious technical challenge on record, and it makes 3 findings. The first is deflationary. Expand the gravity from entropy action around flat space and look at what governs small perturbations, and what you get is exactly quadratic gravity, the curvature scalar plus the square of the Ricci tensor, with specific coefficients. Quadratic gravity is not new. It has been studied for 50 years, and its problems are well documented. If Pereira is right, then in the regime where you can actually calculate cleanly, this theory is a theory people already know. The second is methodological. The restriction used to make these calculations tractable, assuming the curvature is diagonal, is only a reduced subsector of the theory, and it excludes an entire class of gravitational wave solutions. That criticism reaches the Yangzhou black hole paper too, since they use the same restriction. The third is the serious one. Working out the spectrum of the theory around flat space, Pereira finds the massless graviton you would expect, plus a scalar mode, plus a spin 2 mode, with the wrong sign and a negative squared mass. In his words, for the foundational choice of a positive coupling, conventional Einstein normalization implies a tachyonic spin 2 instability. A tachyonic instability means the theory has a mode that grows without bound rather than oscillating. Perturb it, and it does not settle. It runs away. Flat, empty space would not be stable. And crucially, this appears for the sign of the coupling that the theory actually needs. Not some exotic corner, but the standard case. That is the kind of finding that either kills a theory or forces a substantial rebuild. Now let me be scrupulous about its status. It is one preprint, 26 pages, not yet through peer review, no journal reference, and no institutional affiliation listed for its author. It could be wrong, but it is also, as of today, the only serious technical challenge on record in 18 months. And that, I think, is the more interesting fact. There is no published comment on the paper in Physical Review D. There is no rebuttal from a senior figure. When Valinda published his Entropic Gravity, named objections from established physicists arrived within months. A discussion thread about Bianconi's paper opened on a physics forum in March of 2025, accumulated a few thousand views, and received essentially no expert engagement at all. The only reply is the person who started it, answering himself. The theory has not been rejected, it has not been embraced. 3 groups have found it interesting enough to build on. 1 person has found it interesting enough to attack, and the great mass of the quantum gravity community has, so far, not looked up. There is one more entry worth noting, because it comes from a completely different direction and arrives at a related place. In October of 2025, Philip Dorau and Albert Much published a paper in Physical Review Letters deriving the semiclassical Einstein equations from Araki relative entropy, the same mathematical object, applied on a horizon rather than through a volume, and described by its authors as a quantum field theoretic generalization of Jacobson's derivation. Different route, same raw material, and a result in the field's most selective journal. Whatever else is true, the idea that relative entropy has something fundamental to say about gravity is not one person's private conviction, which is exactly what the question we started with looks like when you actually go and check it. 2 hours ago I asked you a question and then refused to answer it. Did this physicist find a new origin for gravity? We are ready now, and the answer has 3 parts. and I am going to give you all three without softening any of them. The first part is that she found a new way to write it. That much is not in dispute by anyone. The action for gravity, expressed as a geometric quantum relative entropy between the true metric of spacetime and the metric induced by matter and curvature, is a genuinely new construction. It is not a variation on something. Nobody had written it before. It is published in Physical Review D, which is the leading journal in the field, and it passed peer review there. It reduces correctly to Einstein's equations in the low coupling, small curvature limit, which means it reproduces every single experimental success general relativity has ever had. Every orbit, every clock, every deflected ray of starlight, every gravitational wave. Its equations of motion stay second order, which spares it the ghost problems that afflict most modified gravity theories. It treats matter and geometry with a symmetry that Einstein's own action does not have, and it recovers the black hole area law as a consequence of integrating over a volume, rather than as an assumption imposed on a surface. That is a real piece of work. It would be a real piece of work if it had come from someone who had spent 30 years in gravity, and it came from someone who had spent 30 years on networks. The second part of the answer is that she found something she was not looking for. A cosmological constant falls out of the mathematics uninvited. She did not put it in. It is not a free parameter. It appears when you rewrite the action honestly in terms of the G-field, and it has three properties she did not get to choose. It is strictly positive, which is the sign our universe actually has, and which a number of well-developed theories struggle to produce. It is small, for a structural reason. The leading term is quadratic, so a small disagreement is squared before it ever reaches the equations. And it is dynamical. It changes as the universe evolves. That is the part of this story I would still find remarkable, even if the rest of the theory collapses next year. In a subject whose most famous number is wrong by a factor with 60 to 120 zeros in it, a theory that produces a small positive dynamical constant as a consequence, from an action written down for reasons that had nothing to do with cosmology, has done something unusual. And it arrived in the same 18 months that 14 million galaxies started suggesting the constant might not be constant. And the third part of the answer is that she did not find an origin. She has not yet. And I want to say this clearly, because she would say it herself, and has, repeatedly. The theory assumes geometry exists. It builds on Einstein's insight that gravity is geometry, and it does not attempt to explain where the geometry came from. That is not a criticism. It is her own explicit statement of scope. But it means the word origin is doing more work in the headline than the paper can support. It is a first quantized theory. It produces modified gravity equations. It does not quantize the gravitational field the way quantum field theory quantizes electromagnetism, which is to say, it does not solve the actual problem of quantum gravity. Asked what keeps her awake at night, her answer is the second quantization of this theory, that is, the open wound, and she names it as 1. As published in the Continuum, it contains no fermions. Every atom in your body is built from particles this version of the theory does not yet describe. The singularity it hoped to soften is still there. Somebody did the calculation, and the infinity survived. Nobody has fit it to a single cosmological data point. There is no paper testing its dark energy prediction against the microwave background, or the baryon acoustic oscillations, or the supernovae. The one thing everybody wants to know, does the number come out right, has not been checked. And the one person who examined whether flat empty space is even stable in this theory found a spin 2 mode with a negative squared mass, for exactly the sign of the coupling the theory requires. And I want to name one more thing, which is not a flaw in the theory, but a fact about its situation. 30 citations. That is where it stands after 18 months. against a body of work by the same author that has been cited more than 20,000 times. 3 groups have picked it up. 1 critic has taken a swing at it. The great mass of people who work on quantum gravity for a living have not engaged with it at all. No endorsement, no rejection, no published comment. It is not load-bearing yet. Nobody's career depends on whether it survives. That is the ordinary fate of new ideas in physics, and it is worth remembering when anyone tells you a paper has changed everything. Most papers do not change anything. The ones that eventually do usually spend several years looking exactly like this: interesting, unrefuted, and largely unattended. So, not solved, not, in the strict sense, an origin, but a new place to stand, and, sitting on the table beside it, a piece of an answer that arrived without being asked for. There is one more thing worth saying about her honesty here. Asked whether the graviton would be emergent in her picture, she said probably not. Fundamental. And then, immediately, she added that it is also an open question whether the graviton exists at all, because the metric can be described using other objects entirely, and you do not have to start from the metric. That is a person volunteering, unprompted, that the central object of her own field may not be there. It is not a common instinct. Now let me come back to the sentence we started with in the middle of this episode. Matter tells spacetime how to curve, and spacetime tells matter how to move. That is Wheeler's line. Every popular book on relativity opens with it, and it has always been read as a description of a conversation, a beautiful reciprocity, 2 partners in a dance, each shaping the other. If Bianconi is right, it was never 2 things talking. It is one thing failing to agree with itself. There are not 2 partners. There is a single geometry, described twice by 2 different methods, and the descriptions do not match. What Wheeler heard as a dialogue was the sound of one disagreement sounding off both walls of the room. And I keep coming back to that flat sentence in a seminar hall in Trieste. No, I will never go into the continuum. She said it to a stranger whose name we do not know, who asked a question that was only obvious from outside. She went home and thought about it, and then she went. And everything in this episode is on the other side of that. The continuum is where the mathematics worked. The continuum is where curvature is defined. She says she intends to stay there, for now. That line is not a broken promise. It is a measurement. It is the exact distance a single question from a stranger can move somebody, and how much they will give up to find out whether they were right about something else entirely. Which leaves the hardest question of the night, and I do not have an answer to it, and neither does anybody else. If gravity really is the strain between 2 descriptions of the same place, if everything that has ever fallen fell because 2 accounts of one location could not be reconciled, then what is doing the describing? The theory needs both geometries to exist before it can compare them. It is very careful about the comparison. It never says where the 2 things being compared came from. The disagreement explains the force. It does not explain the disagreeers. And there is a version of that question you can ask about almost everything we covered tonight. Boltzmann told us, entropy is a measure of what you do not know, but a measure requires somebody or something that does not know it. Relative entropy is a measure of surprise, and surprise is a thing that happens to a point of view. Every one of these quantities is written as though there were a perspective in the world, and physics has never been comfortable saying whose. Maybe that is a sign the theory is incomplete. Maybe it is a sign that the next theory will explain where the 2 geometries come from, and this one will look like a very good description of the second to last layer. That is how it usually goes. Newton described the force, and Einstein explained where it came from. Einstein described the geometry, and somebody, eventually, will explain where that came from. Or maybe it is a hint that information really is the bottom of it, that John Wheeler was right when he said it from bit, and that at the very bottom of the world There is nothing but a difference between two accounts, with nothing underneath either of them. Her advice to her doctoral students, when she was asked, was disarmingly ordinary. Read, study, try to follow what you actually like. Try to express your own vision of reality in what you do. And enjoy it, because enjoying it is part of why any of us do this at all. And her closing thought, in that same conversation, was this: try to look at nature with surprise, and maybe things will turn out nice. I do not think she meant that as a technical statement, but it is one. Relative entropy, the quantity at the center of everything we have talked about tonight, the thing she proposes, is the action of the universe, is precisely, mathematically, a measure of surprise. She spent an interview describing her working life and, at the end of it, without apparently noticing, restated her own theory in plain language. Maybe that is all any of this is, a universe that keeps two accounts of itself and never stops being surprised by the difference. And us, lying here in the middle of it, held gently against the sheets by an argument that has been running since there was anything at all to argue about. Thank you for coming with me on this long walk through gravity and entropy and a question nobody has finished answering. If this is the kind of thing you like to fall asleep to, a like or a subscribe would mean a great deal to me. It genuinely helps me keep making these. And remember, the next time you drop something and watch it fall, you may be watching two descriptions of the same room failing, very quietly, to agree. Good night, and may you never look at falling the same way again.